So far in this course we've talked about linear equations, things of the form y equals mx plus b. We've also talked about quadratic equations, y equals ax squared plus bx plus c, and we even looked a little bit at cubics. So now we're just going to talk more in general about polynomials. So polynomials are things that look kind of like this. Okay, that's not a perfectly good math definition, but the point I want you to see is it's always going to be a coefficient. The coefficient could be 1, so you may not actually see a coefficient, times x raised to a power. Okay, and n has to be an integer, a positive integer in fact. So it's always going to be things like 3x squared plus 2x minus 1, or 7x to the 8th plus 4x minus 2. Anything like that. It's most of what you deal with that's not trig or log or something like that. So the first thing we want to talk about is actually function notation. Okay, function notation. Now first of all, remember that y is the same thing as f of x. Sometimes people get this confused and they think that's f times x. That's not multiplying at all. That's f of x. And what it's trying to tell you, it's just naming the function f, or it could be p of x or b of x or anything like that. It's naming the function with a letter, and it's telling you what the variable is in the function. Okay, so here's the difference. I could say f of x is equal to 3x cubed plus 1. Or I could say f of t is equal to negative 16t squared plus 4t plus 1. So you notice this in parentheses is just identifying what variable we're using. It's telling you what variable the function uses. It could be x, it could be t, it could be pretty much any letter. So that's what it tells you. So the next thing I need to make sure you know how to do is find values using function notation. So for example, if they tell you that f of x, f of x is equal to x squared plus 1, and then they say find f of 2, it's really important that you understand what that means. F of 2 simply means you take 2 and you plug it in for x. If you look, there was an x right here, and now there's a 2 right here. So they've already told you what to do by just literally replacing x with 2. So that's what you do. You replace the x with 2, and you get your answer. So it's really important that when you see that f of 2, or f of, let's do another one, let's do f of negative 3, that you understand what that means. Okay, they have replaced the x with negative 3, so you put negative 3 in for x. Negative 3 squared is 9, plus 1 is 10. So that's function notation. Another way you need to be able to use function notation is to find the value of a function using a graph. So you can see we have a graph here, and they ask us to find 3 different values. We're trying to find f of negative 1, f of 1, and f of 3. So please keep in mind that these are all x values, the negative 1, the 1, and 3, and we're looking for y values. So negative 1 is what we look at for x. So I come right here, here's f of negative 1, and I find that the function is right there. I just follow negative 1 up, and my function is right there. So if you look, that's the y value, 2. So f of negative 1 equals 2. Now next I go to 1. So 1's right here. I just follow 1 up until I get to the function, and f of 1 would equal 4. And then f of 3 is right here. So it's already at 0, so we don't have to follow anything anywhere. We just get 0. So all they're doing when they give you these things is telling you the x value and asking you to find the y value. That's all there is to it. They're giving you an x value, negative 1, 1, or 3 in this case, and asking you to find the y value at that point. Now this moves us on to something else we need to talk about, and that's domain and range. So domain is the set of all x's in a function. And the range is the set of all y's in the function. So let's look at this one and see if we can determine the set of all the x's in the function. Now remember, x's is left and right. X-axis is the horizontal one. So if you look, the smallest x value we see is right here at -3. So I'm going to start my domain at -3. Now if I just keep moving along the x-axis, we continue to have values until we get to 6. The graph stops at 6. So the domain would be from -3 to 6. Now you do have to put parentheses or brackets around these. If, like at -3 right here, it's an open circle, then you put a parenthesis. If, like right here at 6, it's a closed circle, you put a bracket. The parenthesis basically means you go all the way up to that number but don't actually touch it, because that open circle means that you can do -2.9, -2.99, and you can get as close to -3 as you want, but it doesn't actually touch -3. Whereas the closed circle tells you it stops right at 6. So the bracket for 6 means it actually hits and equals 6. Okay, now let's talk about the range. With domain, we move from left to right, starting with lowest on the left to highest on the right. With range, we're going to start with the lowest, meaning up and down, so the one farthest to the bottom. So down here is the lowest we ever go, right there at -4. So we go from -4, and the function continues to have values as we climb up all the way until +4. Again, -4 has an open circle, so we're going to use a parenthesis. +4 has a closed circle, so we're going to use a bracket. So just think again of the domain as being all the x values, in other words, all the values we have from left to right, and the range, all the y values, or all the y values up and down. Let's try 2 more with domain and range. This first one, remember, domain is all the x values, so it's all the values you touch left to right. Okay, well, if we go to the left, that arrow would imply that we never stop. So there's no starting point on our left. That means we have to go all the way down to -infinity. And you always put parentheses around infinity, negative or positive, because it's not actually a number. So you never actually get to infinity, it's just something you approach. Okay, because as we go this way on the number line, there's no limit. We can go that way as far as we want. So that's why we start with -infinity. And if we go to the right, it's the same thing. There's no limit. We can go as far to the right as we want. That arrow implies it just keeps going and going. So we get -infinity to +infinity. Another way you can write that is all real numbers, which can be abbreviated with an R with 2 backs. So that's the domain. Now let's talk about the range. The range is our distance up and down. So start with the absolute lowest point. Well, here's the lowest point right here. It's at 0, and it does actually touch 0, so I'm going to put a bracket. But as I go up from there, there's no limit. It keeps on going up forever and ever, so I put that to infinity. So I go from 0, inclusive, meaning the bracket, all the way up to infinity. One more. Remember, domain is left and right. So let's go as far left as we can go. That would be right here at -6. So it does actually touch -6. Now I'm going to travel until I get to the farthest. Well, if you look, there's no limit. The fact that the arrow just keeps going means that I will never have a limit to that side. So I'm going to put -6 to infinity as my domain. I can't go any farther left than -6, but I can go as far right as I want. Now let's do the range. Let's see, as low as you can go. Well, there's no limit to how low you can go. This arrow says you can go on forever and ever. So we'll have to start with -infinity, because there's no lowest point. It just goes down forever and ever. And then we'll travel up, but the highest we can go is right here, and that's at 6. Now if you notice 6, there's an open circle, so it's not included, so we have to put a parenthesis. Remember, open circle, parenthesis, closed circle, bracket. So that would be our domain and our range for this one. Next thing we need to talk about is the vertical line test. The vertical line test determines, or it's a test to see if a graph is a function. In short, a function is a equation where every element of the domain is unique. Another way to say that is you can have more than one of the same y, but you cannot have more than one of the same x. And an easy way to test this just by looking at a graph is with the vertical line test. So I'm going to use this red line that I'm dragging up right here as my vertical line. So the way you use this vertical line, it's actually a little longer than I need. Let's do this. The way you use the vertical line test is you just take a vertical line, you can use your pencil, you can just use your imagination, and you drag it across the graph. If at any point that vertical line touches more than one point at a time, the vertical line test fails and you know the thing is not a function. So as I pass this across here, I know immediately I'm in trouble because I'm hitting a point here and I'm hitting a point here. And if I'm hitting more than one point, then it is not a function. Okay, so that first one looks like a football is not a function. Now let's move on and look at the next one. Okay, well as I pass through here, I seem to just be hitting one point at a time. And so I'm good. This passes the vertical line test, so is a function. Any straight line that's not vertical should be a function. Okay, let's pass over this one. Appears we're just touching one point at a time, one point at a time. Alright, we're good there as well, so this is a function. Again, we're looking to see if there's ever a time where the vertical line hits more than one part of our graph. Okay, as we move this way, we're good, we're good, we're good. Oh, we've clearly got a problem here. We're hitting it in one point up here and at one point down here. So since it hits more than one point, we can clearly say that this is not a function. Okay, now this graph's a little unique. Okay, well I just hit one point there, that's fine. Just following this line. Okay, it looks like I only ever hit one point at a time, so this is a function. As long as I don't hit more than one point with my vertical line at a time, then it is a function. The last thing we need to talk about today is whether a function is increasing or decreasing. And we talked a little bit about this when it came to quadratics, because we figured out that we could always determine where something was increasing or decreasing as long as we knew whether it was up or down, and if we knew also where the vertex was. Now if we're dealing with something other than a quadratic, that's a little bit harder to know. But what we want to focus on is being able to determine it by looking at a graph. So we're going to be using intervals again, just like we do with domain. So here's what I want to do. I'm going to first identify where this is increasing and where this is decreasing. Now I'm going to mark all the decreasing parts with red. So that would be from here all the way down to here. And then from here all the way down. Those would be the spots where I'm decreasing. So let's try to describe those spots. Well, it starts, let me back up. When we're talking about increasing and decreasing, we will always use intervals with x values. Okay, so you're always thinking in terms of the x-axis. So in other words, as far left as I go, this is always decreasing. No matter how far I zoom out, as far left as I go, this is going to be decreasing, going downward. So it starts at negative infinity. I know the graph starts way up high, but I don't care about how high or low it is. My point is where I am on the x-axis, where I am left and right. So as far left as I go, this is going to decrease all the way until it gets right here, which is at 0. And for these, we just always use parentheses, because really right at those spots where it changes, it's neither increasing nor decreasing, so we'll just use parentheses. Okay, then it picks up and decreases again, starting at x equals 2. So notice I'm using x values, x equals 2, and then as far right as I can possibly go, so to infinity. So it also decreases there. So decreases from negative infinity to 0 and from 2 to infinity. So let's mark the part that's increasing with blue. That is increasing from 0 up until 2. Again, it's vitally important that you focus on the x values. Must focus on the x values. Okay, next example. There's one other possibility besides increasing and decreasing, and that's that something is staying constant. So I'll use green for that. So you can see this part, if I had drawn it a little better, it'd be really easy, but it's staying constant, doesn't move. And then this part is increasing. So as far left as we go, as far as I can go this way, all the way until 0, I'm going to be constant. So it's constant from negative infinity until 0. You might be able to put a bracket there since it is actually constant at the point. I would accept that either way. And then from 0, starting right here, all the way out to infinity, it's increasing. So constant from negative infinity to 0, and then increasing from 0 to infinity. Let's look at one more. Again, I'm going to do increasing parts with blue, and decreasing parts with red. So as we start on the left, notice it just goes on forever and ever. It's increasing starting at negative infinity and does so all the way till x equals negative 2. So increasing from negative infinity until negative 2. And then it starts increasing again once you hit 0 and does so all the way over till 2. Okay, so from x equals 0 to x equals 2, it's also increasing. Now red, we go from negative 2 to 0, focus on the x value, negative 2 to 0, and from x equals 2, and then on that way forever, so to infinity. So that's how you use a graph to identify where something is increasing or decreasing. The last thing we actually need to do is talk about max and mins. So I'm going to use the same three graphs we just looked at and talk about max and mins. Now, to be clear, we're going to be talking about relative max and mins. So relative max and mins. That means it doesn't have to be the highest point on the whole graph or the lowest point on the whole graph. It just has to be at a peak or a valley. So for example, we have a relative minimum right here. It's the bottom of a valley, for lack of a better word. And we have a relative maximum right here because it's the top of a hill. Okay, it's not the highest point because you can see this goes on up forever, and this isn't the lowest point because that goes down forever, but they're the lowest and highest points in their neighborhood, so they're called the relative max and min. So we would have a relative minimum at 0, 0, and a relative maximum at the point 2, 4. So these are points. We're using ordered pairs again. I know it's confusing going back and forth between ordered pairs and intervals. I wish there was a better way that they had to notate this, but they don't. This is just the way everybody does it. So the minimum is at 0, 0, the maximum at 2, 4. And you can have more than one min and max, just so you know. This doesn't have a clear one, so we're not going to worry about it. Let's look at this one, talk about max and mins. We have two relative maximums, here and here. So I have a max at the point negative 2, 2. I also have one at the point 2, 4 as another maximum. And then a relative minimum right here at 0, negative 2. So a relative minimum at 0, negative 2. And if you notice, this one right here is actually a relative max and the absolute max. There's not a point higher than that anywhere on the graph. So you could call that a relative max and an absolute max. So that's what we need to know as far as graphs of polynomials. Page 228 through 231 has some great examples to practice this with.